this talk is a little bit different. We're covering less about a specific product and more just about a couple of abstract ideas and components that are starting to become more popular in the machine learning space, that are less about developing and tracking the models that you build and more about the next step of the process, how to take the models that you're building and to put them into production in a reproducible way, with data lineage and tracking and scalability in mind as you go about developing your systems. So quick about me and then an agenda. My name is Ben Epstein. I'm the machine learning lead at a company called Splice Machine. We try to focus on a lot of these different components, but today we'll be talking more generally about these pieces of technology, how they work, and some different approaches that people have taken to implementing them. So we'll be talking about production machine learning, how you take your development and experimentation systems and put them into production. We talk about why that's hard to achieve, and then we look at some of the solutions that people have put in place in order to take those kind of difficult steps and make them a bit easier and more streamlined. So some of the goals of production machine learning, some of the things that we're trying to do when we are building models to put them into production in a workspace or in a company or for a product, are to increase productivity. So what does that mean? It means making the data scientists on your team more productive in the building of those models, having them do less infrastructure work, less data munging and cleaning, and really get directly into the development of those models, the hyperparameter tuning of the models, the research into the data that they're doing, building out new features, all of the stuff that they find very interesting. When I got to speak to some engineers at Uber, and they've been pretty open about the fact that one of the hardest parts of their productivity line is the managing of the features that are actually going into the models as opposed to the models themselves. And we'll talk a little bit more about that in a bit. So productivity is very important. Another piece that's really important is improving the accuracy of your models, right? Not just the performance metrics when you're building those models, although that's very important. You want to make sure that those models maintain their performance over time and are quickly retrained when they lose that performance, when you have concept and data drift in your systems. And finally, something that's not necessarily thought of as much as the other two, but is extremely important, is data lineage. How do you guarantee that you know exactly what data went into a particular model in production? If a model makes a bad decision, if you get audited, or if your system just starts to kind of blow up and you need to investigate that model, you can use HTAP and Lime to understand why the model was making the predictions it was making. But you also need to understand how the data changed, the data that went into that model, what it looked like before the model was trained, what it's looked like since the model was trained, and what it looked like at model training time. So it's extremely important to understand what data went into it and how that data was created. And try to add on to that production machine learning, it gets even more difficult if you want to take those production systems that you're building and make them real time. It's one thing to take a model and to train it every night or every week or every month on a batch set of data, but it's even more difficult, and these problems become even more apparent if you want this model up all of the time with high availability, able to respond to problems in milliseconds. And these are really common issues, right? Customer experience, customer calls, dealing with issues as they arise in a customer support setting, detecting fraud or a failure in a manufacturing plant, or even just recommending products on something like Amazon or the next word on Google's email AutoML or auto suggestion. It becomes even more difficult to keep these systems up and in place if you want models responding in milliseconds. And we start to think about, why are these problems hard, right? We have so many different tools for machine learning, so many different tools for experimentation and modeling and notebooks and pipelines. We have all these different systems. But when you want to build a real-time machine learning system or a production-ready machine learning system, you sort of need a full gambit of tools. You need a modeling environment, which we've seen today in a lot of the talks, a place to build your models, scale the training of those models. We need an experimentation hub where you can track what went into models, the hyperparameters of those models, the thousands of different runs that you built to actually create the models that you created. We need a location to deploy those models. So where are those models going to be hosted? How are they highly available? How scalable are they? How many predictions per second can they make? Something that's kind of new in the space that we'll talk about is a feature store. So it's really important. The feature store gives you reusability and governance of the features that are going into your models. And then you also need operational data layers, right? You need an analytics platform, maybe something like Snowflake to handle massive scales of data as your data gets ingested into the system. And you also need an operational data platform, right? If you want your models to be ready to make predictions as those predictions are necessary, not maybe days, weeks, or months later, right? In a real operational system, you need a high performant, fast database to access the data that you need for predictions. And the problem is, in today's landscape, we have a lot of support for some of these pieces. We have an incredibly large number of modeling environments, right? We have Kubeflow, we have Google Colab, we have hosted Jupyter notebooks, we have GPU support companies that offer GPUs as a service, obviously TensorFlow, Keras, scikit-learn. We have an incredible number of ways to build models and scale the building of those models. And likewise, we have a lot of really powerful tools for tracking the experimentation of those models. We have Kubeflow, we have CatSeed, which we just saw, we have DVC. So we have a lot of different tools to say what went into these models, how do we know the actual architecture, the guts inside of the model that we'd like to deploy. And this might be hard to see. This is half pink and half gray, this deployment layer. We have some really strong support for the deployment of models, but that support isn't always fully encapsulated, and we'll talk about that. There are some components that have been managed for you, like the infrastructure of deploying machine learning models and the scalability of those models. You can find those sources, but it's not necessarily always the full suite of what you need. And then there's a lot of good support for scale-out analytic data platforms as they relate to machine learning. You could think of Snowflake, or you could think of Delta Lake from Databricks, a lot of really good platforms that are for analytic processing. But systems that we don't necessarily have today in this space dedicated to the machine learning architecture are a scale-out operational data platform, so something that's giving you your data at incredibly fast speeds tied to the deployment and management of your models, and a feature store. These are starting to become very popular, but there isn't an industry standard yet for feature stores in this space. And another one of these problems is that when you're trying to piece together, when you're trying to build out your machine learning workflow for your team or for your company, or even just for yourself, there are an incredibly large amount of components to choose from, right? I think everyone will have recognized almost all of these icons in each of these spaces, but there are just a few too many decisions to make, and it's very hard to kind of bring these together into a cohesive, unified system, right? There's a lot of duct taping and wiring together to make these pieces work as one. And one of the problems that happens when you end up with this many components in a stack is you end up with these bespoke pipelines. You have your data warehouse, or even your real-time data if you're at that point, or some database out in some other team, and you start building these pipelines. Maybe you're using Airflow or NiFi or Kubeflow pipelines, whatever it may be. You start building these ETL systems to go into each of the models or the dashboards that you're trying to build and deploy. And so what that may look like is you may have a pipeline that pulls data from a real-time data source like Kafka, and potentially a data warehouse, maybe something like Snowflake, and it brings those two data sources together, and it makes a bunch of calculations that are necessary for the features into the machine learning models that you're trying to build, and that gets fed into a particular model. Maybe a data scientist is trying to build a model that's predicting fraud, and they find that the moving average of the last 180 days of spending per customer is a very useful feature. And so they make that calculation statically, they put it into their model, and they want to go ahead and take that model they built in Jupyter and deploy it into a real world setting. But we have to now get that feature. We have to get that feature that was calculated statically from all of these sources in order to feed that model when it's actually deployed. And so you build a pipeline to do that. And potentially somebody else simultaneously is trying to build a model that's predicting customer churn. And they also find that the 180-day spend moving average spends of a particular customer is helpful in predicting churn. It's the same feature. And they predict that statically, or they calculate that feature statically, and they're ready to deploy the machine learning model that they've built. And so something they might do is also reach out to a data engineering team in their company and ask them to build a pipeline that pulls data from a data warehouse and their real-time source maybe in Kafka, make that calculation for the past, send them all the data, they can train it, and then keep that data pipeline running so they can feed this model in production in real time, either in real time or on a daily or batch basis. And what happens is you end up building a lot of these bespoke pipelines that are duplicating the computational load necessary to create the same feature over and over again. And this is really bad because what happens is you end up with A, higher computational costs. So you're spending a lot of money to do the same thing over and over again. B, you're recreating features in a lot of times in a very manual process. And what happens there is that you end up with a large capacity for user error. It's very easy to have written a bug into one of these pipelines that's feeding a particular model that may be written slightly different in one way than another, and it may lead to slight changes in the value of that data, and that can be disastrous, right, if you're trying to build hundreds or thousands of models to put into production for your team. You also end up losing signal because you're duplicating these pipelines, and sometimes the computational cost might be just so high. You may have so many of these pipelines that you can't use every feature that you want to use in your system. And you may have to cut out some of the features that you want in your model, and then you end up with less signal-based models, less accurate, less performant models. And finally, it becomes a data lineage nightmare. If you are building hundreds of data pipelines to feed just a dozen or so models, it becomes very, very difficult to track what each value of each data point was when it was fed into a particular model at a particular time. And as the team that you're building grows, as you put more and more models into production, this data lineage, this tracking of pipelines to features to models to training becomes more and more difficult over time. And so with those problems that we're looking at here, with these pipeline duplications, we entered the feature store. The feature store is a system to kind of reduce the computational load, to reduce the pipeline duplication of your system, and to really organize and be a data layer between your data warehouse and all of your data stores and your final machine learning models that you're training. So a feature store is, like I said a second ago, really a line in the sand between a data science team and a data engineering team. It sits between your raw data from your data warehouse or your analytic database and your production system, your real-time key value store that's feeding your machine learning models in real time, as well as being used to train your machine learning models. So it really sits in between what a data scientist interacts with and what a data engineer interacts with. And a feature store provides, four main services. It provides the ability to search for new features. So it provides a single source of truth for your data scientist to come in to say what kind of features have already been created, what pipelines already exist that are feeding the feature store, what are the trends of these features, how have they changed over time, what are the distributions of these features, to create training data sets. So once you've picked a set of features that you want and potentially picked a label or taken a label from outside the feature store often manages the creation of training data sets in point-in-time consistent ways. We don't have time to go into how the point-in-time consistency works in this conversation, but what's worth noting is that it ensures that when you're creating training data sets, all of your features align with the correct point in time of your label. And the way to think about that is to say, what were the values of all of these features at the time the model would have been making this prediction? So when 2 weeks ago my model was predicting fraud, what were the values at that point in time of every single feature? And that becomes very complex to figure out when all of your features are changing at different cadences. So the feature store manages that aggregation for you. So that's the kind of offline training side of a feature store. And then what a feature store also provides is this real-time serving of data points into a machine learning model. So if you create, for example, a feature that's 180-day aggregation of your data values, and you want to take that model and serve it into production, how do you get that value in real time as predictions are being requested, as you need to make new predictions? What isn't feasible is to recalculate those features every single time you need them, right? Because they may take minutes or hours or days even to calculate. But with the feature store storing all of these features for you in a governed way, you can immediately access the most recent value for every one of the features that you have. And finally, governance. So feature stores, not all, but most, manage the actual pipelines for you, but almost every feature store manages the change in values of features over time. So if you have a particular feature, you can see what that feature was yesterday, you can see what it was 2 weeks ago, and then see what it was a year ago. And with that information, you can get distributions of data, drifts of data values, and really have a full end-to-end view of what's going into all of the models that you build. And so we looked at a second ago, a diagram with a lot of bespoke pipelines feeding different sets of models with a lot of duplication. But when you have a feature store lying in between the models that you're developing and the data warehouse and the raw data that you're gathering, it really becomes a single point of entry, and it really declutters the data feeding into your machine learning models. You can create, for example, a few pipelines that have very similar features in nature. So for example, I may want, like I said before, the 180-day moving average of customer spending. But I may also want the 60-day and the 30-day and the 90-day and even the 3-day. And I can create a single data pipeline that feeds into the feature store that calculates all of those values once every however often I'm interested in that being calculated. And now if I have a data scientist trying to predict fraud, and I have a data scientist trying to predict churn, they can just come to the feature store, see a single source of truth, a single set of features that are available, and create a training data set with any of the combination of those features that they want, train it, know that they're getting the most up-to-date values for those features, and then take that model and put it into production in whatever way they need. And so we talked about this, but just to kind of harp on that point, a feature store really is meant to provide 4 things. It's meant to enable data scientists to discover all the features in the space, even ones that they didn't necessarily know about. Helps them create training data sets from different sources when they're ready. It enables really fast millisecond serving of those features. This may not be necessary, but as you mature in a data science organization, oftentimes teams really want models to be making real-time productions in the line of business. And a feature store kind of sets you up to be able to do that from scratch. And it provides end-to-end lineage, which is extremely important, as we know, if models start to go awry, if there's drift in your systems. So maybe asking, this is really cool. This is all kind of in theory. How is this possible? What do I need to be able to create a feature store that does this? And yeah, there are a lot of pieces and a lot of components that go into a feature store. And with that comes a lot of different requirements. So a feature store needs to be able to be have both analytic power, being able to run those batch kind of aggregations, like we keep saying, 180-day aggregation moving averages. Those are large computations. They may take up a lot of resources. Your feature store needs to have the engine to be able to do that. It also needs to be able to scale to billions of different feature values, right? Your feature may change every 10 minutes, and you may have this feature store running for years and years on end. So it needs to be able to scale to billions or trillions of records. If you're using it for real-time feature serving, your feature store needs to be able to access the features that you need, get feature vectors that you're interested in just a couple of milliseconds. And it needs to create those point-in-time consistent training data sets like we talked about. A lot of feature stores today offer really nice tracking abilities and really nice governance abilities, and even automation of feature pipelines. So I define that I want to calculate this particular thing, and I want it to be calculated every day from this source. A lot of feature stores will actually manage those pipelines for you, although you don't have to. And a lot of feature stores that do manage those pipelines will also offer backfilling of new features, right? Because if you have a feature and that feature is calculated maybe every 6 months, you get a new value for it, and you decide that you want it today, you're going to have to wait a really long time to be able to get all of the previous value, or to get enough values to use it into a model. But if you can take that feature, define how it's calculated, and tell the feature store to backfill that feature on all of your historical data, you can immediately use that feature and all of its historical values into any machine learning model that you want. So backfill is a really awesome tool for coming up with new ideas for features and using them immediately. And so two of the things that are really important of a feature store, which we touched on, is really fast serving of features into production, and also being able to do large memory scale aggregations and analytics on raw data to be able to create these features on a batch type of basis. So you can think of this as something like Snowflake and something like Redis for your key value store. And a lot of feature stores today are built on these two architectures. This what they call an online store, which is a common term for your streaming or your key value store, and your offline store, which is thought of as your data warehouse. And this works pretty well if you're doing your training data, or you're feeding into you're feeding your pipelines into your feature store. That is being managed by your data warehouse. And so you can do your large analytics, you can do your large aggregations, you can create these training data sets by doing your joins and your where clauses and your window functions. These are often built in SQL databases. And you can feed the feature store in that way, and that can go to the consumer. And when you're serving your features in real time, oftentimes you'll have this dedicated key value store distributed maybe in memory database. And that will offer you your extremely fast lookups, right? This is explicitly used for the newest values of every feature to feed a machine learning model that's either in production or ready to go to really quickly serve them, even if it's for a dashboard. And there's these two separate entities that are sort of working together and being managed as one system inside of a feature store, which works most of the time. But there's one sort of problem that occurs with this architecture. And the problem is that the story of consistency between these two systems. What happens when you have one dedicated offline store and one dedicated online store is it becomes up to your feature store service, if that's an endpoint or a REST API or an application that's running, it becomes the responsibility of the feature store to manage the continuity and consistency between these two systems. And this is an extremely difficult problem. It's effectively asking a feature store service to become an ACID compliant intermediary layer between two independent data stores, right? If you have a pipeline that is feeding your feature store and you're a user that set up this pipeline, to you, the data is just going into the feature store. But under the hood, the feature store needs to ensure that that new value that's coming in has been added both to the online store for feature retrieval and the offline store for training. And how does it do this, right? What if one of these pipelines fails halfway through? It goes into the online store and then it crashes, right? Now it's in the online store, not the offline store. Or it goes into the offline store first and then crashes. Or there's a glitch and some incorrect value happens, or the whole system shuts down. How do you ensure that these two stores are always identical? And the short answer is you can't. It's extremely difficult. In developing the feature store that we're working on, I was really lucky and able to talk to some of the really big tech companies who were sort of pioneering feature stores. And I asked them about this problem. I said, how do you ensure this consistency between the offline and online store? And one of the engineers I was talking to laughed and said, this is the problem they haven't solved yet. This is one of the most difficult problems that they are trying to solve, and they're trying to come up with innovative solutions around it. But it's extremely difficult, if possible at all. And so coming into the space is this alternative approach. There's an idea out there that's gaining popularity called an HTAP database. And what HTAP stands for is it's hybrid transactional analytical processing. And what that means is it's a single database, it's a single engine, a single store of data that is able to do both transactional processing, meaning fast key value lookups in millisecond time, and out of memory analytic processing. So being able to do things like massive Spark jobs or maybe even Dask jobs if it was for some reason built in Python. But the core idea of an HTAP database is that it's able to do both sides, this online and this offline store, in a single engine. And if that database, for example, is ACID compliant, which many, many databases out there are, this is a potential solution to that problem. This enables you to have a feature store that is powered by a single source of data. And so what that may look like in practice is you may have your batch and streaming data that's coming in real time, or that's coming in on daily or weekly aggregations. And you may be running massive aggregate jobs on this data. And that data is feeding into your feature store, which you may be transforming and ingesting, either managed inside or outside the feature store. But at the end of the day, it all goes into a single database. And this single database makes sure that your online and offline store are consistent, because there's only one offline, there's only really one store. They're maybe separated logically, but really under the hood, it's just one set of data that's always the same for online and offline. And this can go both into training of data and to serving of features. And so this, in my estimation, will become more popular in the feature store space as companies scale with feature stores and start to see these problems of data consistency between the two stores. And the way that this HTAP database often works is that there's something called a cost-based optimizer. And again, we're talking about relational databases. Feature stores are often on structured data. And in these relational databases, you issue SQL to these engines under the hood, whether that be through the API or directly at the feature store, at the underlying data store. At some point, SQL is often being written and executed on. And under the hood, if you have very fast lookups, for example, this is a where clause on a select statement, so it's just a key value lookup, that query goes to a cost-based optimizer, which can make a decision if that query is analytic in nature or transactional in nature. And those two engines under the hood work together to manage any of these different computational or query-based needs. So it's a really cool system. A lot of HTAP databases are coming out now, and I'm expecting that a lot of them will start to implement feature stores, or people will implement feature stores on top of them because of that capability and that loss of problematic, that loss of problem when it comes to data consistency. So that's really cool, right? We have talked about and seen an example of how a feature store may work in general and how it may work with an HTAP database. But either way, when you have this feature store, you have solved a lot of the problems of a production machine learning system. You're able to go to a single source of truth for data. You're able to manage the machine learning pipelines that you're building to feed the data that ends up feeding your machine learning models. And you're given governance about how features have changed, how you access those features, and what they look like when they go into the model, and how they've changed since they went into the model. And just to pivot a little bit, now we're going to talk for a few minutes about deployment. And in that beginning slide, deployment was half pink and half gray. And the reason for that is that deployment today is really powerful, and it's really scalable, and it enables you to take your machine learning model and make it available through an API to the world. But a lot of these systems are sort of ephemeral. They're sort of, ephemeral. They take a set of data or batch sets of data. They return to you a bunch of results, and that's sort of the end of it, right? They're very stateless in that nature. And the problem with that is you need the results of the predictions of your models. You need not just the results, but you need everything that went into that prediction to create that result. And what do I mean by that? I mean, when you have a model running in production, it's crucial to know what features went into that model for this particular moment in time, for the decision that it made, and what decision it made based on those features. It's not just enough to have an endpoint that returns results to you. It's crucial to be able to have all of the history of all of the predictions and all of the features that went into the model as it's been running in real time. You need that to track data drift. You need that to track concept drift. You need that to compare to new models if you're doing A/B testing or rolling deployments, blue-green deployments. And it is really important for auditing. If a customer or your boss or anybody comes to you and says, why did it make this particular decision? You can have the full history of all of the inputs and outputs to your model that you can query, that you can analyze, that you can aggregate on, that you can build analytics on top of. Excuse me. So it's extremely important to have all of those persistent stores. And so, there are some methods that are available. One method may be that you set up all of the components that, you set up a model and you put it to a REST endpoint and you use a Lambda function that calls that model. And the logs of that model are taken and put into something maybe like CloudWatch or some log storage mechanism. And maybe you have a transport mechanism that waits for logs to appear and pushes them maybe into a blob store, an object store, and maybe a database store so that you have persistent storage that's cheap and you're able to analyze it. And this is one method that is commonly deployed to be able to track all of the history of those models. And this definitely works. This is one way to do it. But another way to do it, which is becoming really popular, there are a lot of open source solutions to this, is something called database deployment. A cool open source solution to this, I have no affiliation with, but I think it's cool, is called MindsDB. They enable you to take your machine learning models and put them inside of a database. And what that means is that as you add data to your database, which is where your data would be stored anyway, you can take machine learning models and apply them as tables in the database. So your data comes into the tables, and then the model can be invoked right then and there on that data. And since it's a table, it's storing all of the inputs and it's storing the predictions. A tool like MindsDB is super cool. It doesn't work for real-time deployment. It's not, it runs on a lot of different databases. It's not meant for like real-time systems, but it's very, very cool. And I think it's going in the right direction in terms of the way to kind of combine your data and your models, to bring your machine learning into your data, right? We've been taking our data and hitting this sort of ephemeral endpoint, but you can kind of take that and pivot it and take the models and actually just put them where the data resides. And I think this is also something that's becoming more and more popular. A lot of databases are starting to support this type of deployment mechanism. And this sort of enables you to not have to worry about any of the infrastructure necessary to take your machine learning models and store and persist all of the results and inputs that went into it. And if this system, if your database deployment is combined with the same system that's running your feature store, you end up with a really, really nice full kind of full story and end-to-end lineage example. Because what you can do is you can have your data streaming into your feature store, which is both serving your machine learning model development because it's in the same kind of data store. You can build your machine learning models right there on the data from the feature store. You can take those models, you can deploy them into that same data store if you're able to deploy your models directly into the database. You can persist all of the inputs and outputs of your models. You can serve those models from just another table, which may be your feature store for really fast millisecond serving. And the outputs of your models can go directly back into this store. And it may be the case that the output of one model may be a feature that's an input to another model. And so if your models are stored directly in the database, you can easily set up a system where the predictions and the outputs of your models are fed directly back in as another data source into your feature store for this sort of end-to-end feedback loop, keeping track of all of the systems and all of the components in play between your models and your feature store and all of the data that's going into it without ever really having to leave the system. So this is a really powerful architecture and a powerful kind of mental model to think about how to take your models, your machine learning models, and deploy them and create a full end-to-end system for keeping those models alive and healthy and tracked kind of as your team grows. Cool. Cool. So that's the talk. 4 minutes over, but I appreciate you letting me on and sharing my thoughts on this topic. I really am passionate about the subject. I think it's a really cool one, and it's going to grow as sort of the space matures.
Oh, very cool talk. Thank you very much. A lot of materials, a lot of things to think about, and I'm sure that that many people face the similar problems with feature store and understand that the feature store, the good feature store can actually solve a lot of problems and speed up the deployment and model development. So we have a few questions. The first one is, could you recommend an open source implementation of a feature store which can be used in the end-to-end system?
Yeah, so that's an awesome question. I would say a really popular open source feature store right now is called Feast. Feast does a lot of the systems. It doesn't have the full gambit of requirements for necessarily a production feature store, but it does a lot of the core components of what a feature store needs to do. So it's a really great place to start and kind of see how you can design a feature store that you need. Some of the limitations are that it doesn't support an offline store. I know that they're building that now, but you sort of have to bring the data in with timestamps, but I know that they'll probably develop that soon. And they don't support the pipeline automation and governance, but I'm sure they'll build that out as well. So I would say Feast is a really cool tool for open source feature stores.
Another question is how to determine which feature should be added to the feature store and which should not.
Yeah, so that's a really good question. And it really comes down to your business needs. A potential way to frame that question is how to group different features together. So if you have a feature that's valuable to your model, it should go in the feature store. There's no reason why it shouldn't. Any system that is a feature store should be fully scalable to the number of features that you want. You may have tens of thousands or hundreds of thousands or millions of features. And as long as they're all useful to your system, there's no reason they shouldn't be there. But when you're organizing features, because the second half of your question is adding each feature could result in sort of a regular database with a lot of tables. That's definitely true. Under the hood, a lot of these feature stores are implemented as databases with tables. But the important piece about the feature store, the important layer, is it's sort of a data layer. It's not just regular tables, it's sort of managed tables. So if you are properly grouping these features together, so for example, you're not putting maybe customer demographics with customer spending history in the same grouping of features. In the feature store terminology, it's called a feature group or a feature set. If you're grouping logical features together in those sets, it does kind of look like it does kind of look like a database table, but that table is managed and statistics are being calculated for it, and data drift is being calculated for those tables. So it's a good comparison to think of it as a table, but they're a little bit more managed.